So basically, this is continuing from the last couple weeks, and it's trying to figure out what types of quantum technologies can be inserted at different types of existing technologies. The term quantum is familiar for quantum sensing, and obviously with computing, it's getting a little bit more mainstream. But MRIs and lasers are technically considered quantum sensors because they operate on principles of quantum mechanics. So it's a really exciting field. So we still have people coming on here. Be interested to hear everybody's background too. We'll kind of find out towards the end. I took a lot of this in grad school with analytical chemistry and microscopy, fluorescence. It's a very advantageous tool. And most of these that I'll be talking about use fluorescence, and some might surprise you with super resolution, as far as it's called the Jablonski diagram. How it looks compared to kind of how many of us were taught in school. So again, very important for analytical techniques here. So more people are going to be filing in, and then so we're going to switch over to this guy. So again, this is episode 48. I'm CEO Kevin Kotchak, presenting on, it's basically organoid imaging improvements, what can be improved with quantum technologies. So in that regard, here's an introduction. So I'm going to go over basically a little bit about organoids. It's very fascinating the more you research this, the way they look like almost human body parts. And then biological imaging, that's actually that picture right there. And we're going to talk about scales and, million, micro, nano, those types of things as well. And then obviously all of this depends on the study of light or spectroscopy. So if you've ever taken nuclear magnetic resonance training or MRI training, CT, all these things are either radio waves, X-rays, UV vis, some microwave, IR, Roy G. Biv, or red, orange, yellow, green, blue, violet. And in specific, this field is a lot more established than it has been in recent years. So a bright field microscope is basically an enhanced regular microscope. The image below is basically what you could buy on Zeiss, Z-E-I-S-S. They're imaging just like Nikon or any of these other ones. And then we'll talk a little bit about EM. So this is like SEM, TEM, these types of things, a little bit about micro CT. Now, the interesting part is just the news continues to come as far as quantum imaging, quantum sensing, and the industry as a whole. So again, the term quantum, is quite common in sensing. Like I said, it's not a new thing. The diamond quantum sensors are the newest ones out that have perhaps the best potential behind them. But it's one of those things that will be implemented in technologies such as these. So a brief overview of organoids. So in 2009 and 11, they found intestinal organoid, kidney organoid in 2013, and these are considered adult, like grown. And this is basically, if you look at Zeiss's website, it's basically, okay, they're really serious about offering this equipment to the people doing this research. Now, the one that I'm most concerned about would be cerebral organoids or brain organoids. And the one that was most interesting are these optic cups. So it's kind of looks like a human eye if you zoom in. So we're talking, milli, micro, nano scale with a lot of these things. So we're over to the right. So you see the mouse at 10 centimeters. And then a lot of these kind of hospital techniques, so positron emission tomography, magnetic resonance imaging, ultrasound, these types of things are for, more coarse. Now, the ones that we'll be focusing on the most falls under fluorescence. And in specific, so you see, we'll cover optical, OCT here, wide field, turf, and then the ones that gets the most press are super resolution. Now, these things in theory are awesome, but the stronger the laser, the more photo bleaching. It's just an inherent problem, more photo toxicity. So there's other techniques to getting away things as far as setting up like sheets to scan certain things. So people are beginning very creative in their approach to avoid the photo bleaching while still getting super resolution. And we'll be talking about Palm and Storm a little bit too. I was told in grad school the biggest thing when you go to name an instrument is you pick a cool name and then you work backwards. So I'm sure that's not always the case. So this is a 101 here. So this is basically what we experience right now, all of us. We're in the presence of radio waves, you know, and this is basically in the AM/FM range, and this is what MRIs and, you know, CT scans run off of. So microwaves, what we, you know, is rotational, so vibrational is infrared, and then you have Roy G. Biv. So a lot of times in fluorescence, basically you excite at a higher energy and then emit at a lower. So it's usually green to red, green to red, green to red all day long. And then in UV, you know, that's a lot of times if you start at UV, then you'll end up in, you know, one of these other ones, not so far to red. X-rays, which is CT scans, gamma rays, which are getting, you know, up there as far as, you know, we don't want that type of radiation. And then even further down is called cosmic rays. Now, the scale here that mostly going to be talking about milli, micro, nano, and pico. In this field, when you're talking about resolution, you rarely talk about pico. You know, it's more like if you have individual molecules that you're testing at picomolar, these types of things in chemistry. So for this, most of these instruments are either micro or nano. So milli 0.001 and then micro, nano, pico. So this is the zoom up of what I showed you before. So we're going to be talking a little bit about the point scanning laser confocal module. It's actually the most common among all of these techniques. And then also you have the Palm. So Palm gives you super resolution. So in any of these things, the EM-CCD cameras, this is like the next generation of your CCD cameras. So it's an area where quantum might start to move into too, with diamond quantum sensors, these types of things. But figure, take your CCD and then it's electron multiplying of that. But this is basically what they say is one of their better systems that they sell. So this, many of you may be familiar with. This is when, you know, you first experiment with microscopy. Our family had these all over the place. I've taken one apart. A little bit later, I've worked on SEM before in industry. So it's in this case, it's just mirrors, right? So when you look at these, try not to get confused. So if this is like looking straight at that microscope, as the light source shines up from the bottom through the specimen, and then up through the top is where your eyes are, where it says primary image. Now, the point with this is it's a very simple. Microscopes like this have been around for a while. Bright field has made it better, but basically there's drawbacks. You know, you're shining the light through the bottom up, right? You don't need staining. This isn't fluorescence, but it's just your really crude. If I were to hazard a guess, even if you were in a high-tech lab, you would still have one of these around, just because. And you saw in that Zeiss is basically, you know, it's important to have a backup. But you do, you know, you can record at real time. I've been in industry using these, and there's a little camera hooked up to it that took pictures. I don't think live video. So there's basically steps as you want live video, 3D or 4D. I'll get into that type of stuff too. But the disadvantage here is resolution, and you only get things in 2D as the specimen, that green is kind of laying in the middle there. Now, introduction to fluorescence. Now, most of these things use fluorescence microscopy. The advantage is a lot. So you get both structural and functional. So if you have an MRI, you would have to have MRIs for structural and fMRIs for functional. Now, qualitative and quantitative is good because people want quantitative. You want to be able to count. And then it also has good spatial and temporal resolution. Now, as with anything, you can get photo bleaching, phototoxicity. So it's just how strong this is the laser. And you see, this is, you know, the blue, ground state goes up to the first or the third triplet state here. and then it emits, and then you get fluorescence, and that's what you see. So you're shining in a laser, and then you're getting back light at a lower energy. So just an inherent limitation is if you have low light, you have low signal to noise ratio. Now, wide field fluorescence microscopy, don't hear too much about. It has limited 3D, right? So if you want 3D, live image, no phototoxicity, these types of things. So it's basically higher resolution than bright field, which is just your standard benchtop. And then you'll hear about this a lot. So you'll start to get into super resolution when you go beyond the diffraction limited optics. And then in this case, it's not fully quantitative. So there's some drawbacks there. Now, LSCM, laser scanning confocal microscopy, is thought to be the most popular of all these techniques. Now the 4D, what that relates to is basically temporal and spatial resolution can be tied together. So in those two domains, that's what 4D means, okay? And again, the more fancy you get with these, the cleaner your sample has to be. It could basically, you have a lot more prep going into these types of things. And then in this specific case and in other ones too, if you have real fine lasers, it takes a while to image. So what's best on paper might not always be the best for your specific circumstance if you can't get a super pure sample, or you don't have time for sample prep, those types of things. Now, this one I thought was the most interesting, spin disk confocal microscopy. So basically what I'm talking about is imaging. So this is imaging for organoids. And in specific, so you see this plate moves around, so you get rapid acquisition. So for instance, with organoids, high organoid throughput, and then you can use this for cell division, cytoskeleton, cell migration analysis. So all these techniques are specific to what you want to do in the lab. So you see the green going in, and then it shines down through the beam splitter to the specimen, and then it comes up, and that's fluorescence, and then you have red, and then you're, in this specific case, it's saying it's only using a monochrome CCD camera, which is basically an old kind of thing. So this is actually 2022. So you'll see these EM CCDs. There's another one out there too, but basically if you're looking at imaging, and these are small things, organoids, and then all the way up to humans, as we've seen with diamond quantum sensors, is basically trying to figure out, what could make these technologies better. Now, disadvantages in this one is that, you have pinhole crosstalk, and then if you have a strong beam, and then you get these effects of photo bleaching, phototoxicity. Now, multi-photon microscopy is actually, several of the techniques use this. It says it's more reliable than the Lscm, which is the most common, and then simpler light path, and it's excellent for 4D. So spatial resolution means pixels. So high spatial resolution would mean, high res. And then temporal, without going into detail, basically means that it's faster because you go someplace and how long does it take to go back? So you want both high spatial and high temporal. And in a lot of medical instruments, you don't get both at the same time. Some are good at high temporal, some are good at high spatial. So, and again, with a lot of these things, the more fancy you get, and if you want that one awesome image as opposed to high throughput, it could be painstakingly slow. TURF is an older one. So this image here from DeMuro et al. So 2004 is basically, you cut back and then you get less photo bleaching, less phototoxicity. And again, some of these are good for specific use cases like single proteins. And it says live cell imaging on this one. Now the disadvantagement is low dynamic range, and then it's only for the surface of cells. And LSFM light sheet. So this is what it seems like is going on here is basically on the top is more like the physical image, and then on the bottom is actually what's going on with the light as it passes through mirrors, and then you could see the light sheets going back into the detector. So all of these use detection, sensors, these types of things, and they've, like I said, increased dramatically as far as all these using fluorescence. So this is the disadvantage. I talked a little bit about this, is your samples having to be really pure. I've had this issue even with a standard microscope, is bubbles getting in the way, and then they say the resolution below cellular is not very good, and then it's also creating a lot of data. So this is also an area for quantum technologies. So if you get into, I'll show you later, so it's medical imaging, all the steps to it. If you have something that would take advantage of CPU, GPU, now you have a QPU for specific tasks, a quantum processing unit, those types of things. And then this is the one that's really interesting. So as you can see, this is from Zeiss's site. Now, when I took analytical chemistry in college, I don't remember ever seeing 5 singlet states going up that high. And then, so again, it gives you absorption times, how many seconds, it's really fast, right? These types of things. And then inter system crossing, this might be phosphorescence. That's typically how that is. But basically it's showing, because of all these things, and in specific, it's that STED 3D PSF pattern of, basically getting to higher energy levels, from 0, 1, 2, 3, 4, 5. And then, as you can see, the red coming back down. And it says, I mentioned this before, this is a huge limitation for most microscopy, is overcoming the diffraction barrier and, getting good nanometer resolution. So in all these, and, fluorescence, and I'll talk a little bit about electron microscopy, which is a little bit less practical, they're getting a lot better with fluorescence these days. And then this one, so we saw STED in the previous slide, is some of these use, technologies of other things too. And, a lot of these things, it says no specialized fluorophores. Now with all of these, you're talking chemistry too. So in order to fluoresce a molecule, it has to be certain, conjugation of double bonds and all these types of things. And then there's issues if you're trying to get multiple, colors out of your experiment, not just red. And I'll get to some of those too. But basically, this one says maybe not need that kind of quantum computers as far as specific things to reconstruct images. I'll get to an MIT algorithm. It's basically on. It was done by Seth Lloyd, another company. And basically, they are proposing this reconstruction algorithm, which is one of the steps in medical imaging. So disadvantages here, you do get the photo bleaching and phototoxicity, and it's just a general statement. Anytime you have high energy lasers and delicate samples, there's a balance between great images and not destroying your sample, like live biological samples. And in this case, it says vibration is an issue. And they also say it's multicolors hard to get to as well. So in this one, you'll see the multicolors here, so SMLM. And then in this specific case, it's, 2020. So, you could see where, okay, so samples up, and then you see detector is the EMCCD, that's what's detecting all of these things. And then you have the opportunity to incorporate other wavelengths of light. So it's super resolution, like with many of these that I'm discussing now, 3D super resolution, 3D tracking of fluorescent labeled. So when they talk about tracking, they're talking about time experiments, like doing things over time, which if you've ever done physical science, working in a lab, you want productive studies that show things are reacting, changing over time. Now, so this is Palm and Storm. So Palm, I believe it's the same instrument pretty much, but Palm uses photoactivatable fluorophores, and Storm uses photoswitchable dyes. And then in both cases, they were right up on that chart that I showed initially as far as the level of super resolution. So long image acquisition time is not quite desirable. And then, this is one of those ones where the high quality fluorophores, these chemicals that are incorporated into your samples, need to be good. Extensive processing, and it's difficult for live cell imaging. So this fancy thing can't do live cell. So its advantages is single molecule images, and these are probably more like polymers, biopolymers, probably nothing too small, because in the previous kind of image, it said that it's a little bit outside the range of even super resolution, like a nanometer, those types of things. So this one's interesting, SIM. So it's this whole Moire pattern, and I wasn't able to get to study this too much more, but you'll see this type of thing. And a Moire pattern was you see in B. So there's some advantage to that. So the other things is basically twice the resolution over traditional fluorescence. And then, like with other things, you could experience photo bleaching, phototoxicity. So OCT they say, is the up and comer. So this is the one, basically longitudinal research in same sample. So this means that you keep your sample over time you're doing studies. No resection, you don't have to resection or process the tissue samples, and you get live imaging, long-term tracking, and label-free. So this is probably one that's very desirable if you want to show not kinetic studies, but studies over time, how things are happening. Now, disadvantages are you can't do specific things like the internal structure of transparent samples due to the physics of it. And there's a contradiction in the image depth and resolution. So SEM, I've used this instrument before. We've had, I swear it was an older instrument, but you can replace certain parts of it. Basically, this is in a vacuum chamber, so you can't have samples that are volatile. They have to be solid compounds, like salts is what I typically do. But these create absolutely beautiful images. If you've ever seen kind of like the EM images of something really up and close, it's SEM's typically the way to go. As you saw on the chart, it's way off to the 1 nanometer, these types of things. So finest resolution, larger depth of field than TEM, which is on the next slide, 3D topography. And the disadvantages is, like I said, you can't have biological living things in it. So there was actually a picture I saw with this, but in theory, we're talking like liquid nitrogen cooling. Well, that's for a different part, but in theory, it's a very kind of strict thing that's for solids. It also destroys things, and it's only for the surface. So this is the other EM, transmission electron microscopy, and then it's similar type of issues as EM. And then micro CT, so I don't know how many of you are familiar with CT, so computerized tomography, and CT is used for patients, and it's basically X-ray, and it rotates around the patient or the sample. In this case, you see the tissue in there, and then so it goes around, and then it goes through, right? So X-ray is higher energy, so it goes through, and then you have detection. And I've seen them use diamond quantum sensors for these, and or they just say diamond sensor, which is probably diamond quantum sensor. But I've seen them used in specific CT instruments. And again, so this whole thing is looking at, different parts of image formation, image computing, creating really nice images, and especially with new quantum technologies. So there's some limitation to micro CT. So if you were able to join last week's, I shared this, and it's very, very important because these are the steps for medical image processing. So you have acquisition, detection, conversion, precondition, and you go through all these things like reconstruction. The MIT says they have these algorithms for reconstruction, so iterative algorithms, and you just see like, okay, what parts of these could benefit from quantum technologies? Enhancement, and then so this is part of image computing, and then in specific visualization, so image data rendering to visually represent anatomical and physiological information, and of course management, communications, sending this data over internet. Now in the news, so smart quantum camera And in specific, this one, it says Abbey-Rayleigh criteria. So on all these things, you're trying to get better pictures. And I was once told, I don't know how old I was, but I was once told, like, medical doctors just look at pictures all day, right? That's radiology. So the technology is all there. So say, for instance, a neuroimaging, makes all these things. And then neuroradiologist looks at the pictures and then offers a diagnosis. So they would always want a cleaner picture. So in this case, we're talking about artificial neural networks and universal quantum model, these types of things. And I wasn't able to spend too much time on this, but I just thought it was interesting because we talk about CCDs, EM CCDs, in either CMOS detectors, these kind of standard things. And you kind of wonder, how will these incorporate over the course of time with quantum? Now, this came out recently. The paper, so on the left is the headline, and the headline's always better than the article, but it's still good news, right? But it says photon bursts boosts quantum sensor performance 100 times. What was previously a nuance may now greatly enhance diamond-based sensor sensitivity. So it's an emerging thing, right? And last month we saw a heart application, we saw a noise reduction application. And then in the article, they say we propose and analyze a simple yet powerful protocol to reduce the detriment impact of readout noise in quantum metrology protocols. So that's basically what this is reducing noise and figuring things out. So these are a couple that the first two have been around. So they say our technique will enable the study of the origin and progression of various cardiac arrhythmias, including flutter, fibrillation, and tachycardia. So that was a Nature article, Japanese researchers. It's probably the one that's getting the most buzz. It has a really good picture. You could take a look at it. Now, the second one, they say, we envisioned that the techniques developed here lay a path for different quantum sensing platforms and achieving low distortion sensing required for many applications in science and technology. So these are in the abstracts, conclusions, typically they're summarizing these things. Now, this one is news. So this came out this month, and they say accurate magnetic field imaging using nano diamond quantum sensors enhanced by machine learning. So we're starting to see all these other established technologies or methods basically to help improve these diamond quantum sensors that can not only be used for magnetic, electrical, biological samples or humans, and then also for temperature. I saw force and I saw strain. It's either strain or shear was the last one. Now, where is everything for neuroimaging and what can you do? So algorithms, it's a key part for this Fermilab NYU Langone collaboration. They're using quantum technologies to make better MRIs. Now, BMC, I've tried reading this in the past. I'm going to try reading it again to see if I can understand it better. And it's basically a quantum algorithm using CT, which is the X-ray thing in the hospitals, for COVID-19. Now, the one I've overlooked in the past is this 2020 quantum medical imaging algorithms. And of course, quantum algorithms run on quantum hardware. And there's not a ton of this stuff out there. But basically, when the hardware gets there, everybody will be like, oh, we can run these now. So in specific, that was for reconstruction. Medical imaging. And then for computing, you've heard me say it 1,000 times, NSF 2023 Practical Quantum Computer, Xanadu, a task this year in June 1st, in 36 microseconds instead of 9,000 years. Quantinium, 2022 this year, significant milestone in error correction, and this has to do with logical and physical qubits. So in networking, US Naval Research Lab, the NRL, basically says we will have a national quantum internet. Harvard and AWS, I think this past week or this past 7 days, they formed a quantum networking research alliance. And then also Fermilab and Argonne transmitted both classical and quantum data over fiber optics at the same time. So the call to action or mission statement for Chemical Q device is to improve neuroimaging techniques utilizing quantum technologies for better sensitivity, signal strength, and or resolution, leading to advanced prediction in neuroradiology for Alzheimer's disease. So this is primarily going to focus on sensing algorithms and computing for techniques like MRI, PET scan, and CT. So just a cool couple quotes. Every once in a while, a new technology, an old problem, and a big idea turn into an innovation. So this is so I wrote down, I'll find the quote later, basically who they are. So the other one, Theodore Levitt, creativity is thinking up new things, innovation is doing new things. So I thought those were very kind of interesting there. Are there any questions? I could keep the slides up for a little bit. I saw a number of people joined on a little bit later here. So basically what I just talked about is basically organoids, and then the instrumentation, specifically fluorescence behind the organoids, and kind of the pathway with new quantum technologies to make these better. So better resolution, spatial or temporal, better signal to noise ratio, those types of things as well. And I see that we have a number of people that have been on before. So we have Sonu, we have Philip, Dave, and then anybody that's hasn't been on before, you can come on too.
Well, Kevin, I'll just make a comment before the new guys join. Once again, you've done an amazing job in providing probably the most dense and accurate information available in the medical field around a particular theme that can benefit from quantum. And it's just wonderful to be able to see this. What comes to mind is Ron's comment from last week, where all this tech seems to be a modern version of the Star Trek visor, Geordi LaForge visor, which is basically a really cool pair of sunglasses, but they operate as an optic nerve. I see Philip there with what looks like a Star Trek-esque background. Philip, is that what we're seeing right there?
Hi there, Dave, and hi, Kevin. This was just, such a useful talk. I have no doubt that I'll come back to it and watch it again. This is a fantastic overview of all that tech. Thank you very much. And Dave, nice to see you and to hear your ever entertaining discourses.
Well, it's good to see you, Philip. There's two Philips here, though, and we have a new Philip with whose last name I don't know, who has the Star Trek-esque, who's about to let us know if it is Star Trek. I see him nodding his head. Oh,
yeah, that Philip is muted.
Yeah.
You're muted, Philip.
Your mic, Philip.
Thank you. I apologize. Yeah, it reminds me of the Discovery, but it's just a random background chosen from a space station.
Oh, Dave was hoping it was specifically regarding the Star Trek.
It looks like Discovery, but other in the colors.
Yeah, that's a version of Star Trek. I'm with you on that. And for Philip N, good to see you. You always look like some sort of person out of the movies when I see you right now. You're like some sort of, I don't know, PhD guy from the movies. And Dr. Faisal Shah Khan says, hello there, by the way, Philip, and to you too, Kevin. I was just having a board meeting that was letting him know about what you put together. So it is something that we talk about to our epidemiology lab. So you're legendary.
Yeah, I appreciate the comments and the feedback. So epidemiology, the study of disease, basically, right? How to make these things better. And yes. Obviously, a lot of these things are tied together. And even with this national quantum internet, it could be a huge impact in transporting data, even with intranets and smaller hospital systems, these types of things, to help patients. But yeah, I would say the thing that kind of really sticks out is definitely the diamond quantum sensors. It's just pretty much every week. So if I were to think two big ones last month with the heart and the noise reduction. And then this month, there was an EV battery, and basically they said using this diamond quantum sensor from 2 different directions, they were able to achieve better sensing of the state of the battery, like the percent. So that was a big one too. I didn't put it in here because I had other kind of medical ones that seem more relevant. But in any of these cases, say if it's the EV battery that they're using, 2 sensors for, maybe that could be used in medical applications and those specific things. So it's the type of thing where it's just, I haven't, because NIST published a video on, in 2009, NIST published an article saying that they thought you could take these diamond quantum sensors and put them on tips of rods and use them as mini MRI probes. So I didn't find too much between then and 2021, but in 2021 they found out the algorithm in this basically for this fluorescence that we've been talking about, where the green shines and then emits this red light. Well, they found the algorithm to look at the red light more closely to determine what's exactly going on in the presence of the sensor, i.e. the patient, the rat, the whatever. So after 2021, it seemed to really open up some stuff. And there was one other one too. Oh, the machine learning one that I shared too, that you're going to have all these other AI was with the quantum camera, so that was interesting too. So Shai, you have a question?
Hi, yeah, it's great to join everyone, and I got to apologize for a couple of things. The first thing is that I was on a business call and had to join late, so I'm sorry to have missed a big portion of the presentation that I would have liked to have caught. I also have a general question, and this seems like a good time to bring it up based on the topic of the discussion. I should say I'm not a scientist. I run a division of an executive search firm, which is essentially headhunting. We're the first executive search firm to have a division entirely dedicated to quantum technology. So I'm not unfamiliar with quantum. In fact, I'm very much into it, but not to the level of a quantum engineer or a scientist. So when I ask this question, it's coming from the point of view of, to some degree, a layperson. There are 2 types of quantum optics and imaging that I've come across in the market. The first type is actually talking about a lot of what you've talked about today, is talking about how to image, for example, medical imaging, so neural imaging and things like that. But there's another kind of quantum optics and imaging that's been referenced in the market by various companies. One in particular is Oxford Instruments, a British company. And when they refer to quantum optics and imaging, they don't seem to be talking about the same thing, medical imaging or neuro imaging or anything like that. They're talking about detecting single photons and essentially recording single photon events. So my question is, are there 2 definitions to quantum optics and imaging, where one of them is related to, quantum entanglement, detecting single photon events, and another separate type is medical imaging and using quantum sensors to produce, images of, say, for example, very intricate, tiny areas of the human body? Or are they somehow, tied up one with the other, rather than being separate and distinct separate definitions of what is essentially the same verbiage?
Yeah, as far as the single photon, some of the stuff we covered during the slides is the same kind of thing: single photon, multi-photon detection, these types of things. Now, the clearest thing for quantum imaging, now quantum sensing is a big part of quantum imaging. Now, the other ones, the other big one is called quantum ghost imaging, and it's those types of things where it's just like something can sense something that it didn't even sense it to begin with. It's a really kind of like, entanglement, or it's more like quantum teleportation. It's just one of those things where it's hard to wrap your mind around. Now, the other ones are called quantum lithography, stub-shot noise imaging. You'll hear about a fair amount. Now, the distinction between the 2. So I had shared, I don't know if you were able to catch it, Shai, it's a website called Analog Devices, and they have the whole breakdown of medical image processing. So in those, in specific, you have image formation, image computing, those types of things. Now, I think your question was what, medical quantum, what were the two were you were referring to?
Yeah, so they seem to me, from a fairly layperson's point of view, it seems to me like they're essentially referencing two different things. From the medical standpoint, you know, the way you would use quantum optics and imaging in the healthcare setting is one thing where you would use a multitude of different techniques, some of which are not even photonic in nature, some of which are, you know, using different quantum mediums to kind of get to an image of, say, for example, you know, a part of a brain or whatever it might be. Whereas, you know, the other definition coming from, you know, a company like Oxford Instruments, which specializes in, you know, helping just R&D or experimentation, is talking mostly about, you know, single photon detection, quantum entanglement. My question is really, are those the same thing? Are they two different dimensions of essentially what is the same thing, or are they completely separate?
Yeah, I mean, they could be related. When you talk Oxford, it sounds like anything with like the research, so say for like neuroimaging, it's more nuts and bolts, but neuroradiology is more like taking the nuts and bolts and then, you know, getting that image and getting a better diagnosis, those types of things. So yeah, they can, and I would say by the time, that's how I perceive all this is basically if Oxford's doing kind of, you know, smaller scale stuff to understand, they're basically trying to understand exactly what's happening. And I think that the flow is usually like you have to figure out the specifics of something before it starts to trickle into medical. Because with medical, you have approvals, all these types of things. Now, all of those instruments I showed you, these high-tech fluorescence, you know, microscopes, basically, is that, you know, they're not on real patients, they're in vitro. So that's the huge gulf, basically, is when you start to say medical, is typically you're dealing with, you know, you said on a chart I showed is basically you're dealing with bigger sizes, more regulation, those types of things. Whereas like if you have fluorescence and you're dealing with nanometers and SEMs you don't use on people. But yeah, that's my interpretation, is basically a lot of these, you have to start off really small in the lab as far as understanding the mechanics. And then eventually it goes into medical.
Got it. So two different sides of the same coin, essentially. One earlier on in the development process and the other at application.
Right, right. Yeah. So medicals, I mean, there are applications in, you know, fluorescence with organoids. So the whole reason, I don't know if you caught this point, but you have optic cups and you have cerebral, which is brain, you have lung, these types of things, is that you could do whatever you want to these things, right? You can experiment on them. And the whole presentation, you know, basically the first couple slides is trying to get more reproducible organoids. And I read it was a next 50 years of neuroscience, and it was a Society of Neuroscience journal of neuroscience kind of thing. And they said that we will have more reproducible organoids, so the research will get better to understand these things, so we don't have to do an invasive brain surgery on humans, and it's just very limited. Like you're only talking probably thousands of invasives, but the organoids is, you know, really taking off. Growing basically little human body parts in a dish.
Great, thank you very much for that response. I imagine we'll be able to pick up this presentation after it to catch part of.
Yes, you will.
If I may add a little bit.
Where? Sorry, where would we be able to find it?
Yeah, I'll put the link.
Okay.
Yeah, go ahead, Philip.
Yeah, it's just in, you know, in connection with Shai's question, if I understood it, I think the general answer is that all quantum sensing is based on quantum mechanical phenomena such as entanglement, quantum entanglement, and quantum interference. But there are various ways of implementing it, and photons is one of the ways, and there are others too.
Yeah.
Thank you, Philip.
And I don't know if you caught this, Shai, is basically MRIs and lasers are considered quantum sensors. So quantum sensors are not anything new. You can search on the Google, you'll find this thing called PAR, which they use for different like agriculture. So if anywhere along the line it looks like it operated by the principles of quantum mechanics, you can call it a quantum sensor. Now, another good example, I don't know if anybody knows, it's called a Squid MEG. So superconducting, and basically there's only like 20 or 30 of these. It's basically, it's half the size, it's not as big as a MRI, but you sit close to this thing that has to be cooled by liquid helium, and it's measuring the magnetic information from your brain. Now, the problem with that is you have to go to the hospital. It's not room temperature, right? Like you have to bring in other things. California, San Diego has one. You're kind of lucky if you do. So there's this emerging technology called OPM MEG, OPM optically pumped, I think it's molecule, something like that. It uses a rubidium atom. So when it senses the changes of the magnetic field in the patient, then that vector is a lot larger because it can be placed closer to your head. It's not as sensitive as the ones in the hospital, but because you can put it close to your head like an EEG cap, it's favored. Now, the article with the rat's heart and the magnetic information, that they said that it has advantages over OPM MEG. And I wrote a paper on OPM MEG. And I'm like, and it might be out the door. I don't know. But they seem to have claimed that that specific type, this diamond quantum sensor, it has, laser light shining in and different things around it, has advantages over something that is supposed to be replacing something else that, so it'll all play out. Awesome. Anybody we haven't heard from? I know Ron Schreiner.
Sorry, still not sure where the link will be showing.
Yes, I'm copying it right now.
Oh, great.
Yeah, so let's see. So yeah, anybody we haven't heard from?
Good evening, everybody.
Okay.
Hey, Kevin, you talked in your presentation, you talked a little bit about quantum imaging. Is that something that is just associated with the quantum sensors? It seems to me like in this whole process in the medical industry, or this flow of or I guess it's almost like a tool chain. You could have quantum support or quantum enhancement of image acquisition, and then there's also the possibility of using quantum via quantum computing and quantum image processing for for the diagnostic step after the data has been collected. Some of the stuff on the back end I've looked into a little bit, but in that middle ground, I guess were any of the things that you studied in the quantum image acquisition step actually doing anything more than just using quantum sensors, like using quantum noise reduction techniques or something?
Yeah, like I said, AI and ML. So there was one article, AI, one in ML to make these diamond sensors better. Now, the other ones for the quantum ghost imaging, quantum lithography, and the subshot noise imaging, those and quantum sensing, those four fall under quantum imaging. And then you're exactly right. I posted up that chart that shows image formation, image computing. And there's a number of steps that you could use for sensing. You could use for computing later on and visualization. Now, some of these fluorescence techniques, there's just inherent to having a small, really powerful laser that just takes a lot of time, right? So that's not an area to be looked at. But other things like, say, for instance, is a diamond quantum sensor going to be a lot better than the current EM CCD sensor detector kind of thing?
And is that where this all comes together, where these diamond quantum sensors or arrays of them, so to speak, replace the CCD step in each one of those diagrams?
Yeah, that I'm not sure. I'm just saying potential, because I haven't done enough research to find out exactly to say like, oh, okay, this heart one or this specific noise reduction. Now it seems like there's two kind of articles that focus on the noise reduction. So it's just a matter of putting all these things together. And like I said, it looks really bright because not only are people publishing in Nature, but you have NIST solving an algorithm last year, and then they're doing their own kind of analysis of where it could go in 2009. And just to see, the worst thing you want with a new technology is it's promising. Just with computing, is quantum computing's been through it too. I think in 2017, a lot of people thought they were going to solve a lot of things. So it's good to see that this specific diamond quantum sensors is backed basically by big organizations.
All sounds very interesting, and I'm sure there's way more opportunity for things that can be had with these diamond quantum sensors than just replacing the CCD cameras. But I guess we'll see what happens in the future.
Yeah, and they said also with a lot of these other things is you're going to get hybrids. So just within quantum computing, you have CPU, GPU, QPU, quantum processing unit, and they were saying hybrids to have the diamond quantum sensor to make a conventional technique better, right? So you'll likely see an amalgamation or whatever that word's called. These technologies join together. So, and again, like say for instance, the EV article that said like, okay, we're using this for only vehicles, and then you're learning from it, and they're positioning the sensor in a different way. So, yeah, just like I said, just like with computing, like with sensing, and sensing falls under imaging, all these types of things, is that whatever is the setup that creates the best results, that's probably, and that's not too expensive, that's probably the one that's going to make it. Awesome. So there's a number of people we haven't heard from, and I'm glad that you're on. So Joachim or Mark, feel free to come on. You can unmute your mic or do your video. Sonu is a regular. And then we've heard from Shai, haven't heard from Sion. So no question is bad or wrong, right? And it doesn't hurt to repeat things either, for the other people in the audience too. And then Tim's on all the time. You have anything, Tim?
No, I don't. I actually don't feel very good today, but I'm not that coherent. But yeah, I decided this was important enough. Go ahead and listen to the talk.
Yeah, well, thanks for coming on. Sion, you have anything?
Hi, I didn't have any questions, but I just wanted to say thank you so much for inviting me to this. I'm an undergraduate student at UCLA, so I don't know a lot about quantum anything. So I'm really just kind of getting into this for the first time. I find it incredibly fascinating, and it's through events and presentations like these that I can gain a better understanding. So just thank you all for doing these discussions and having these talks, because I really get bits and pieces, and slowly I'll be able to build my knowledge. Just thank you so much.
And don't be bashful. I mean, there's a couple of people up there. I've gone on theirs, and there's her name's I think it's Clarice D. Arillo. She does quantum biology. And then her kind of stuff, I actually learned a lot from her. So she's a professor at UCLA. She broke it down with everything with diamond quantum sensors. It was a Womanium talk. So you could check that out too. And you might find yourself meeting these people. I mean, UCLA is big. So, and then the other lady, Ashley Fletcher, and then they have quantum discussions for UCLA. So during the school year, they're pretty much once a week, but you could look for those. I would look for those UCLA quantum stuff. And your department is somewhat big. I think it's multidisciplinary, so it's like solely focused on quantum. But the people that are also associated with quantum, there's a picture, check it out on your website there, of like, I think 30 or 40 people on this bridge in UCLA, like an indoor bridge. And so it's kind of cool to see the quantum involvement at UCLA.
Yeah, of course. Could you repeat that name of the first professor you mentioned?
Yeah, her first name is Clarice.
Okay.
And then it's D Aurelio. So it would be CDA or her initials.
Okay, perfect. I'll look her up and see if I can get in contact. Thank you.
Yeah, you're welcome. And again, so feel free, no question is a bad question for sure. And even if this is the first time you've heard about quantum, so don't feel afraid to come on. Philip, did you have something?
Me, no, I'm just gathering information.
Okay. And then Joachim?
Yeah, hi. I just want to say thank you for the invite for this. This popped up on my screen just like less than an hour ago, and I have not been to your previous meetings, but I'm in New York working in financial services, generally not very knowledgeable about this stuff, but trying to pick up some of it. Medical industry is a big mystery to me, but I really appreciate the talk you gave. It's very interesting to know. And one or two people see on the call here seem familiar from LinkedIn. But anyway, this was very informative. I appreciate it. I may not know all the background, or to be honest, very little about the background of what you've been talking about, but it's interesting, fascinating, and thank you very much for your presentation and the invite for it. It was very good. Thank you.
Yeah, and you're definitely welcome. I did a quantum timeline several months ago, and you might find gain in that. If you look at my LinkedIn, it's basically my top 10 for neuroscience, and somewhere in there is it. And you would be surprised the number of financial institutes that are tied to quantum. So last November, last fall, Goldman Sachs, Fidelity kind of posted these articles that says revolutionary, will change things forever, with either a quantum algorithm, and then I forget what the other one was. But you have multiverse computing, which only does kind of financial models. And so that's called the trying to help the Monte Carlo simulation. And they were the ones that they said they had an algorithm that is 100 times better than some other conventional. So that's that company, but it's actually benefiting transportation and finance with, it's called a technology called quantum annealing, and that's only for optimization problems. But that's one of the earlier use cases is for finance. You can't do everything, but it's out there.
Kevin, yeah, this is Mark Bernard. I wanted to ask you about the quantum entanglement, and apparently you're saying there's some use of quantum entanglement for cellular imaging. Can that even be possible? How does that work?
Okay, so you're saying body cellular, right?
I guess, well, I'll settle for any kind of imaging.
Yeah, I mean, and all these things, it just depends on what you're talking about. Now, okay, so where do I start with this one? So basically, when the rat's heart is measuring its magnetic field, okay, and that's what it's doing. Now, in other types of sensing, so for instance, there's an MIT that says it can measure any type of any electromagnetic frequency in the spectrum that I showed earlier. Now, as far as at the cellular level with a diamond or with any quantum sensor, I'm trying to think. So typically they're tied to electrical fields, magnetic fields, force, temperature, those types of things like strain. Now I'm trying to think, have I seen anything? I saw an image of, they did use diamond quantum sensor on a brain, right? So those are neurons, and so they're for sure people have, and even in this NIST video, they said that people are going to likely use it for brain applications too. So in that case, you're measuring either electrical field, which is action potential, which is from electrochemical interactions in the body, or you're measuring the magnetic field that's generated from it. Now, you might have to be a little bit more specific when you say cellular, because there's there's quantum chemical sensors where you excite this to a triplet state, this certain type of molecule, and the molecule is acting like a qubit. So could you be a little bit more specific?
Well, I was just kind of intrigued that you said there was some sort of ability to sense in any way cells. I mean, my interest would be closer to cells or things smaller than that. And so that's what I was intrigued.
Yeah,
I wanted to find out how it would work.
Basically, the study of light is a huge thing. So in all these, the pitch deck I just presented on is basically you have some chemical that when it's exposed to higher energy laser, it emits something, and you measure that light coming off of it. So that's like fluorescence in a nutshell. Now, the specific things in the cell, without thinking off the top of my head, it's a very specific thing. Like, are you trying to, what are you trying to measure? Like pH or, salt concentration, these types of things. So, I'm sure there's applications out there if you were just to say cellular, but so say for instance, like the proteins on the cell surface, doing fluorescence, but instead of measuring with an EMCCD, measuring with a diamond quantum sensor or some hybrid of that, those types of things. But typically, if you want to quantify things, it's typically you're studying light. So you're interacting with like a laser, and then the receiving end of it allows you to quantify, basically say like how much of whatever.
And so you mentioned also the diamonds involved with this too. Is that really acting as a kind of lens? Is that essentially what it's doing, or is it something different?
Right, so the diamond itself, you have carbon, right? So what they do in the lab is they omit carbon and you put it in nitrogen. And then nitrogen has 3 bonds, not 4 like carbon does. So then you have a vacancy right next to it. And then that's your framework. So then when the laser shines in, and whatever it's in the presence of, like I said, either electrical, magnetic, temperature, force, those types of things, is that due to that interaction with the light and the vacancy in the diamond, and then the sample or the biological sample, the light coming off of it will have a certain variation, and due to this algorithm that they figured out last year, then you can better detect that. So yeah, it's just as far as like, I don't know if you're asking for like certain concentrations of certain molecules on the surface or in the cell, those types of things, but it's typically, I don't know, like I said, I can't really answer it any further.
Yeah, I'm not sure if what you're asking, Mark, is are these things detecting entanglement or superposition of something inside the sample? I don't think that's what's happening, but I don't completely understand how these diamond sensors work. But I have seen, and Kevin has mentioned that the void in the carbon lattice acts like a qubit. So I think they're just exploiting that behavior to get this ultra high resolution or sensitivity to an electromagnetic wave. I'm not sure if anything going on in the sample could be called superposition or entanglement.
Stuff that you're thinking about, Mark, might be a little bit further out, because typically studying light is a very easy thing. So you set things up so it makes this certain color, and then you, like, say for instance, if you're counting the number of cells and then you have a fluorophore on it, so this is just like the other stuff I just talked about, and then instead of detecting with a EMCCD, now you're detecting with a different type of sample. But yeah, as far as Ron said, and trying to wrap my head around it, it's as far as like what exactly you're entangling, positioning. Even in, quantum computing is typically that's done in the computer. and then you need imaging, or especially a sensor to pick that up to send it to a quantum computer. So, but yeah, there's specific things that works really well, and that's like studying reflections off things coming from higher energy light. But yeah, any other questions? Did you have anything else, Mark?
Yeah, no, I think that's really interesting. I'll have to look at some of these papers and see more detail about what is going there. It seems like really exotic to be able to have any kind of quantum entanglement or any kind of application to cells and all of it. If that's real, then that could be a really new, powerful technique to go after.
Yeah, and I mean, just off the top of my head, in computing and in sensors like this diamond quantum sensor, you're getting hyperpolarization, and you have like it's called a microwave generator right next to it. You have up, 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 down, or down, down. And then I think it's the up, down that gives you this awesome illumination of light that's better than many other types of sensors. And all of that sitting outside of the patient, the heart, these types of things. So as far as interacting with it, I think it's more like contained in the system, or at least that's how it seems like today.
All right, thank you.
Yeah, you're welcome. And I encourage anybody, just keep researching quantum. Keep in mind, quantum computing might be a little bit out. They are saying with NSF, practical computer next year, but definitely, research communications is hot. Sensing is hot. Cybersecurity, you can get a Samsung Galaxy quantum phone. It's with a quantum random number generator, I think in Korea. It's not for computing, it's just for security. And then you could have Quantinium IonQ help design a key for you that was formed from a quantum computer. So having that in mind, that quantum computers are good at generating random numbers, those types of things. But yeah, just the quotes that I share is, computers without applications don't employ too many people. They have to be doing something in a specific field, and it's hard to do two things, like know about quantum and science or medical, and communicate that. But very few people actually just work on quantum computers. Over the course of time, I don't know, 5-10 years, is that, who knows, maybe the word quantum isn't as buzzy as it is today, and you won't see as many discussions like this, or Washington DC, or Chicago. So Ron goes to the Chicago one. So yeah, I would say embrace it as it is, just because they say next year's it should be really big in all types of quantum technology. Awesome. Anybody else that we haven't heard from? And again, don't be afraid, don't be bashful. It's good practice for me. I have to talk to investors, so I have to keep repeating myself. There's no such thing as a bad question.
I have a comment. I'm actually really excited to hear about the quantum internet development. I think that could be a great milestone in quantum technology to demonstrate the applications for quantum devices. That is something that I thought quantum devices would be exceptionally good at. It's just sorting algorithm, routing traffic. So I'm excited to hear about that.
Any other kind of comments on the national quantum internet?
You don't really want to get me started, do you?
Go ahead. Well, they run on fiber optics, right? So that's a plus. We don't have to rebuild everything.
Yeah, I maybe I'm wrong about this, but the quantum internet will be something. It'll be an animal unto itself. It'll be right now it's used for quantum key exchange, to think that there will be an actual replacement of what we call the internet with some quantum version of it, I don't see that happening anytime real soon. There's so much stuff that has not been resolved in any way, shape, or form about that sort of thing. If you're interested in it, if you go look up the Washington D.C. Quantum Group, a couple weeks back, they had a gentleman who came on and gave a talk about what's going on with the work that's going on in China with their satellite network. And once you realize that all the satellites are there for is to be a source for entangled pairs of photons. The satellites aren't actually involved in any communications. They're just there to generate entangled photons and get them delivered to ground stations. So, and these because they're entangled, the ground stations can be thousands of miles apart. They're entangled. You can do the quantum magic on entangled pairs from at great distance to do things like exchange keys, generate or exchange, do security-based things. The other thing that people keep hearing that quantum computing is going to make all kinds of things vastly faster. Quantum computing itself is not fast. It's brutally slow, actually. It's the quantum advantage that gets you to be able to crack problems that are not crackable or that are not tenable on classical computers. Doesn't mean it's going to do it fast. It's just going to mean it's using a completely different technique to like factor a large number, assuming you can find a quantum computer with enough qubits that are not noisy, that have a low enough noise profile that you can get that done. That's where they talk about, with a quantum computer, you can solve this in a couple of minutes. It would take 9 billion years on classical. It's not because that computer runs fast. It's because it's using the quantum advantage of superposition and mostly superposition in those quantum algorithms. So again, I don't see the quantum internet as being a replacement for that. It's going to be used for other things. There may be, hopefully one thing that'll come out of it is the ability for quantum computers to exchange states so that you can do distributed quantum computing. There again, you're not talking about large volumes of data. You're just talking about getting two quantum computers on different points of the planet synced up and working on the same problem. Okay, so so just keep that in mind. You're not going to get your YouTube over quantum internet anytime soon. As far as that's my thinking. Hopefully, I'm wrong.
I'd also have to agree with Ron. I think from what I've read and seen out there, that the main issue is range. You get decoherence before you get enough range with photons. So the problem right now, and satellites seem to be a little better at this than fiber optics, but the big problem right now is range. And until we get it, it's not really going to be feasible to have a quantum internet anytime soon. One of the other reasons for that is that in order to get that range, you're going to need quantum repeaters at various points within the line. And quantum repeaters are essentially just mini quantum computers. So until we get to fault-tolerant quantum computing at a mature level, it doesn't seem like quantum internet's going to be feasible either. I don't want to close this topic if there's more to say, but since we've kind of digress from imaging into other areas, I do also have a very interesting question that's on a separate topic when, if you're interested in that one as well.
Yeah, just a couple things. I would say the Fermilab Argon, that they're transmitting both quantum and classical information at the same time. I don't think you're just going to have just a quantum, just a quantum internet. Now, the other thing is what Ron was saying is they're slower. Now it's problems that take advantage of quantum mechanics math. Okay, so that's why you're going to have hybrids, because quantum computers can do complex numbers and linear algebra too. But it's the specific ones that is the quantum algorithm that the problem can utilize or can be solved with quantum mechanics. those are the ones. So yeah, I don't think it's just going to be just a quantum internet, because Fermilab is this article, right? Because if they're already, you know, transmitting, and it's in Chicagoland too there. So, and I think University of Chicago's, they're kind of like the leaders probably in the US in national quantum internet, or in quantum internet. And then, so you have British Telecom overseas with Toshiba, and then obviously DCQNet with the Navy Research Lab that says that we will have a national quantum internet. So Shai, did you have another question or topic?
Yes, since we've gone into a kind of more general conversation here, there is one thing that's been on my mind very heavily as we start talking about all of these interesting developments. One of them is the whole discussion around room temperature quantum computing, and by extension, room temperature quantum systems and technologies in general. It seems to me that some of the most advanced and well-funded sources for quantum computing on the planet, companies like Alphabet or Google, IBM, have stuck to their guns on superconducting, which requires high-intensive and massive systems that use cryogenics to cool things, usually via dilution refrigerator. Now, these companies haven't pivoted one iota or changed track one iota since photonic quantum computing has come about. Ion trap, which I understand for some, I'm not sure about Continuum, but for IonQ, they use Doppler cooling at the atomic scale. So they don't really need to get a massive cryo fridge in there. Cold atoms as well, neutral atoms, companies like Cold Quanta also can operate at room temperatures from my understanding, but some of the others can't. Spin qubits can't, topological can't, superconducting definitely can't. Why are these very smart, very sensible companies, and big, well-resourced companies at that, sticking to their guns on superconducting and technologies that require intensive cooling when there are other methods out there to do it at room temperature that hold so many more advantages? I've heard that scaling is easier with superconducting. I've heard that it's easier to kind of create the kind of effects you need, but photonic quantum computing companies make the same claims. So why the supercooling? Why doesn't everyone just shift to room temperature approaches?
Well, have you seen the chart? So for superconducting materials like aluminum, these types of things, is like you have like probably exponentially greater conductivity. Like there's essentially no resistance at that. Now, IBM, I think just this week, they announced they have the biggest dilution for refrigerator. So I'm in the same boat too. Like, why not try to go for room temperature? Now, it's just a matter of like, is it ever going to happen? Like room temperature quantum computing that can scale. Now, neutral atom is another one too. And there's so many companies that we just haven't heard from in recent months. And then we have 2023 looming with everybody saying it's going to be, even the IBM CEO says that we could have practical quantum computing next year. So yeah, I mean, that's the obvious thing, because spin qubit, I think, is 1 Kelvin, liquid helium's 4. So 1 Kelvin is 100 times warmer than a millikelvin, which is what like the IBM, Google, and Rigetti gateway superconducting is. So yeah, I mean, you have a valid point. It's just, is it ever going to happen with room temperature? Now, Xanadu's 216 photonic qubits on June 1st, they said that they did this 36 microseconds instead of 9,000 years. And like you said, IonQ or Quantinium takes limited. So you have a valid point. It's just getting behind the scenes and seeing actually, is it ever going to happen with a room temperature qubit computer?
So Kevin, if Sundar Pichai or Arvind Krishna came to you and said, listen, we want your advice, should we stop this superconducting stuff and switch to photonic or another room temperature approach, or should we keep going on superconducting? What would you advise?
They're so far into it that I don't think they're going to stop. So if you look at their website, but obviously the biggest issue, it's the most powerful by theory. And if they can figure it out, I don't know if you know this, but they switched to a hexagonal layout to cut down on error, but it also cut down on performance. This is IBM. So I don't know. There's other groups, that we go to, other people on this call, and we're like, okay, we have helium and whatever, neon, those types of things. I wouldn't tell them to stop. I wouldn't. There's many smart people at IBM, and they've been through gate-based superconducting. The performance that they're at now is way more. People were just completely writing off the whole thing. It was just wasting the company's money, that kind of stuff. But I would say it's a lot more promising today than it was even a year ago.
And then finally, on that topic, other than the advantages of room temperature, just being less energy intensive and more mobile, one of the things that we've seen people complaining about recently, especially in an article that came out in the Financial Times or Alphaville the other week, is the size. So right now, you need about the size of a room just to house about 100 qubits for IBM. When you get to 1 million, what do you need? A building, a skyscraper? People are starting to question how big these quantum computers are going to need to be if the cryo situation continues. So just for the question of size, photonics doesn't seem to have that much of an issue when it comes to scaling to that level that superconducting does. Do you see size as being an issue for supercooled approaches?
Well, not coincidentally, IBM in the news just brought up 1 million qubits. Like they just said something path to whatever. And I assume that you're aware of all their forecasts, their roadmaps, where they say, I think we're due for 4,000 even this year, maybe for Christmas.
1,000 this year, I think. 1,027.
And then maybe 4K next year. So anyways, they come out with like 2 of them, but one of them's better than the other, and they have about the same number of qubits, these types of things. So what was your question?
So the question is, the recent complaint about quantum computing in general has been that it will need to reach massive sizes. A quantum computer would need to be the size of a building to house that many qubits if the geometric progression continues. I see superconducting as having that problem more than photonic. So same question, but as relates to controlling the size.
Well, I think with the original computers too, classicals, they thought they'd always be stored in these huge buildings too. Now it's been thought the next several years is only going to be cloud-based quantum computing anyway. This is primarily Briquette, Google, and Microsoft. Now, obviously, every technology that has great potential has a tendency to shrink. But without being behind the scenes and seeing what's going on in people's minds, if there's just that caught up with something that's just that minute that will never get solved, but they don't know that, it's hard to tell. Ron, did you have something?
Well, two things. So the original question is, why isn't Google chasing that? Simple answer is, look at what is their business model. They want everybody to buy every possible computing service from their cloud. So they're not motivated to make room temperature things available where people could just bring them home. My other question was for Shai. You mentioned that there are people out there building true room temperature quantum computers with true room temperature qubits.
Yeah, that's right. So photonic quantum computers like Xanadu's and like PsiQuantums are fully room temperature. There's absolutely no need for supercooling at all. There are other kind of intermediate approaches. So IonQ, for example, uses cooling, but only at the atomic scale. So they use laser cooling or Doppler cooling, and you get the right level of cooling, but you don't need a macro cooling environment to do it because they use lasers. And then I'm not really sure how neutral atom work, but they can operate at room temperature as well. Maybe Kevin knows a little more about how they operate at room temperature.
Not specifically, but the big things is, so Honeywell Quantinuum said that they expect a powerful quantum computer in 2025. I think Google said 2028 or 2029. a useful quantum computer, and obviously NSF, practical quantum computer next year. Now, keep in mind, NSF was the first to fund in the early 1980s, and then these are like more mathematical proofs. But at that same time, the government, or quantum is the government's initiative. The industry's involvement is based on the amount. They're so far into it. If you look at quantum.gov, there's 21 government institutes. If you put all these things together, as far as I don't know if it'll be, obviously DARPA would want it in the field to heal soldiers, these types of things. But if you put all these things together, as far as is it going to be room temp, those types of things. Now, the neutral atom computing, they said that I think they have the highest coherence, or one of the highest coherence in the industry. That's what they're known for. And there's a number, we haven't heard too much from Fujitsu. Japan just came out with that heart sensor, the diamond quantum sensor, that was last month, and they announced their first commercial quantum computer too. So it wasn't much, maybe 10 or 20 qubits, but if I were to hazard a guess, it's a lot better than many other ones out there.
Well, Fujitsu's is superconducting as well, I believe, right?
They're annealing. I think Ron, right, like digital annealer.
They do that as well, but they've got an actual gate-based quantum.
And keep in mind, D-Wave, you want to look at the companies that have been in quantum for a while. So D-Wave has been around since like 1999. Now, their original goal was to focus on gate-based superconducting qubits, and figuring these things out within, I think, a year, they switched over to quantum annealing. Now, in 2011, they commercialized the quantum annealer. And then ever since then, they say they want to have, like they're hybrid today, CPU, quantum annealer, and then also gate-based superconducting. And I think they keep pushing it back. So I thought they said by the end of this year. I think it was at the end of this year.
Yeah, they announced recently that they're going to be switching to a gate-based model. Essentially, they're falling in line with everyone else because they realize annealing's going to be a thing of the past when gate-based comes along. It's interesting also to note, Quantinuum, even though it's a trapped ion technology, I've heard on the grapevine that unlike IonQ, they do actually utilize a macro cooling system for their quantum computer. They do actually use something like a dilution refrigerator like superconducting, even though they use trapped ion, whereas IonQ uses laser cooling. So I don't know for sure, but I've heard that on the grapevine.
Yeah, that very well could be. Was there anybody else?
I think IonQ uses laser cooling to get them the last few degrees of Kelvin down to the state where they need to be, but it's still pretty cold. They call it sympathetic cooling.
So are you saying that IonQ also needs supercooling at a macro scale, like a cryo fridge, before they do the laser cooling, so it's not room temp?
It may be like 10 Kelvin is what they run at, but that's still pretty cold. But they use the sympathetic laser cooling to get them to the way it was stated was that they using the sympathetic laser cooling, you can easily force the trapped ion into the ground state without making it cold. But they've already taken it down into the very low Kelvin, and then they're using the lasers to get it to the last step, essentially.
Yeah, keep in mind, there's always a helium shortage. So helium, I think you can only get it when you're mining for methane, right? So that's like the off-gate gas. It's like 0.0000 in atmosphere. So there's always this push for less helium, like in MRIs, they'll do like a point something percent helium just to get you somewhere. So helium's 4K, nitrogen 77. So nitrogen's easy to get. There's like 70, whatever, 80% in the air. It's helium that's a problem. So that could be another push too, is there's issues of people's NMRs, MRIs in their laboratory. It needs to be constantly cooled. The magnet is always on. And when you run out of the helium or nitrogen or both, it ruins your instrument like $500,000. So yeah, that's usually the push. What's confusing is the IBM is pushing even more towards it because they're announcing now they have the world's biggest dilution or at least in the US. So there's a whole field in cryo. Like there's people that just only want to do cryo stuff, like millikelvin. But I hear you from a practical standpoint, it doesn't make sense, but there's so many, you know, Rigetti, Google, you know, IBM, as they keep pushing. So it does have the theoretically highest performance to solve any problem of any type. It's just
Helium won't be a problem, assuming they get these fusion reactors online and producing electricity at some point in the future.
Oh, is that the byproduct? Is helium?
Yeah, take hydrogen and smash them together, and some of what comes out of it will be helium-3 and helium.
Oh.
But you know, this is where fusion and quantum come together. The phrase is in fusion is fusion. It will always is fusion is 30 years away from being solved, and it always will be. Some people are saying the same thing about quantum, so we'll see. But yeah, I mean, if they fix the fusion problem, helium
Yeah,
should be
and I
pretty
guess
rare.
to cap this off, unless Philip or Tim have, last week we talked about the diamond sensor quantum computer by Quantum Brilliance, and that's what diamond sensors, they can do everything kind of thing. So I think they were at 2 qubits for $5,000, and that was a while ago. That was like 6 or 9 months ago. So, but yeah, any other last questions or comments? Then if not, this is episode 48. Appreciate everybody coming on. Today is September 15th. Have a good night. I appreciate all the comments and the new people too. And have a good rest of your week. Take care. Bye.
Thanks, Kevin.